Hello, so this is a presentation that I gave recently at my school, and I was thinking to actually give it, so to speak, one more time here for my channel, because this is related to some of the. Well, first of all, this might be interesting for those of you who watch the math modeling course that is uploaded on my channel, or those of you who took or my students and took this course and might be interested in the topic. So this presentation is about one interesting result from an older paper that I published in 2016. But some of the insights from that paper, I think, are worth revisiting, so to speak, in light of the current interest with the SARS-CoV-2 pandemic. This is about, as I mentioned in the title here, the law of unintended consequences in epidemiology. Because many times when you implement a measure to turn the epidemic for the better, for example, to reduce the number of cases or to eliminate the disease, often, as with many interventions done not just in epidemiology but in many areas of science or in public policy, if you want, one can always or should always expect possible unintended consequences, which some of them could be actually unusual. In a way. So I'm going to actually start by giving a brief motivation for the title, because the title is kind of general. Most people may think about examples from economics, I think, when they talk about the law of unintended consequence, but in general it's just about interventions done to solve a problem which may cause a worsening of that very problem, or the cancellation of any benefits of that intervention. So just to anticipate what is going to be in this paper, in this presentation, the intervention is going to be the introduction of an imperfect, partially effective, in other words, vaccine. So a vaccine that works only to an extent, in the sense that vaccinated people can still be infected, although at a lower rate. And also we're going to take into account the risk behavior associated with this introduction, which we'll talk about soon. But outside of epidemiology, examples of this unintended consequence concept, like I said, come from economics. Some of these examples. For instance, if in an inflationary, when a country is facing inflation, if there are wage increases or indexing of wages across the board without any productivity increases, often that across the board increase may cause a worsening of the inflation rate, and then that can lead to what is called, I think, a wage spiral, wage price spiral. This actually happened in my home country, in Romania, in the 90s, when we had triple-digit inflation. Now, notice that in this particular example, the unintended consequence, it's maybe not that surprising, and actually the net result may not be negative. So it's all about how much the inflation will increase in response to a wage increase. So I mean, if, for example, the wage will increase by 6%, but the inflation will only increase by 3%, you can still have a net increase in the income, in the purchasing power. But often, of course, it's the other way around. The inflation may increase at a higher rate than the wage indexing. So that means your net result will be a loss in purchasing power. But I mean, this is just about an unintended consequence in the sense that inflation moves in the wrong direction, essentially. What's more interesting, and just to kind of allude, to the main result that I'm gonna talk about later, what's more interesting is that sometimes the unintended consequence is like a 180-degree turn, in the sense that one feature which was positive before may become detrimental in a certain situation. So this example that I posted here, maybe it's less known, but you can Google the information and you'll find the information, or the Wikipedia article about it. So after 9/11, as most people know, the cockpit doors in airplanes were reinforced so to prevent being broken. And at the same time, the ultimate authority of unlocking the door is from the inside of the cockpit. So before 9/11, the um, flight attendants used to have also an ability to unlock the door. After 9/11, the pilots could lock the door from the inside. And as it happens in this flight, Germanwings flight 9525 from Barcelona to Düsseldorf in 2015, the co-pilot committed suicide by plane, essentially by first locking himself while the captain left the cockpit for a short while, and then he crashed the plane. And then, on the voice recorder, you could hear actually the captain trying to break the door desperately. But of course, the reinforcement worked as intended, and it didn't break. And so, in this case, you could say that the intervention would be, let's say, the removing the ability to unlock the door, but that made the reinforcement to become a liability, essentially. So, in that particular situation. My third example will be kind of like a funny one. It's called the Cobra effect. Apparently, a while ago, long time ago, during colonial time in India, apparently there was this infestation of snakes in the city, and the authorities placed a bounty for every snake hunted and killed. Sure enough, this worked like a charm. No more snakes on the street, but then the people quickly realized that they can still collect the bounty if they actually bred the snakes in some hidden farms. And then, so as soon as the authorities realized this and they stopped the program, then the farms released now the worthless snakes on the streets, and then everything was kind of back to square one. So before we get to the actual epidemiology part of the actual presentation and the subject related to the main subject of the presentation, which is related to the epidemiology. Once again, I want you to keep in mind this subtle difference between a unwanted consequence in which just a feature moves in the wrong direction, but the feature is still the same, like nothing really changes fundamentally in the system, if you want. From a situation like in the case of the Germanwings flight, in which a feature just becomes a liability all of a sudden. So, as far as my rest of the presentation, we're gonna split this into several parts. So, those of you who actually watched my or took the modeling course, some of the first part might be really familiar, but I'm not going to assume that. So I'm going to spend a while to just explain briefly how epidemic models are built and the meaning of the famous epidemic reproductive number, which most people actually, even if they are not familiar with courses in math biology or epidemiology, probably heard quite enough from the news because of the current pandemic. So we're going to talk about the meaning of this or not this epidemic reproductive number, and then we're going to move on to the actual paper that I will present, which deals with, like I said, risk behavior first of all, due to an imperfect vaccine, then the concept of cumulative risk-taking, and then the unintended consequence, which will be revealed, so to speak, toward the second half of the presentation. So for the explanatory part in the beginning, I'm going to use what I called textbook models because the actual model in the paper leads to complicated expressions which are not that easy to follow from one slide to another. So I find it always useful to just establish the main concepts with textbook models, in the sense that models which are very simple to follow because they are simplified so that they contain just the minimum required variables and quantities to illustrate that concept, but otherwise without any other extra features, which make them obviously less realistic but much easier to follow. So the general structure of a continuous population model, which is the main tool that I use in my research, is given by differential equations. So for each type of population in the model, the equation essentially gives you the rate of change of that population per unit of time. So on the left side of the equation, you have essentially a derivative, and on the right hand side, there's going to be something that comes in and or out from the population. So the input minus the output. Positive contribution, negative contribution per unit of time. So of course, if you have a demographic model, you could have a birth as an input, death as an output. You could have transfer from one class to another, from one population to another. Like for example, in the case of epidemics, you have infected people appearing as a transfer from susceptible to infected, recovered from infected to recovered, and so on. And one of the most basic population models, as easy as it gets if you want, but still good enough actually to talk about reproductive number already, not an epidemic reproductive number, but the reproductive number in demography if you want. It's this differential equation which just takes into account the per capita birth rate and the per capita death rate. So just a single equation, P is the population at time t, and then you have the birth and the death rate given as, like I said, as per capita rates. So even if you don't follow any, or if you didn't care about any differential equation or math for that matter, intuitively everybody will realize that if the birth rate is greater than the death rate, the population will grow, and if the birth is less than the death rate, the population will decline. Now you can rewrite the same condition, the inequality, in form of a proportion. Beta over mu greater than 1, which is the same as beta greater than mu. But I want to point at this moment that this simple rewriting is not just for the sake of it, just because you want to write the math in a different way. As it turns out, a rearrangement of the terms will lend itself often to a way to interpret that quantity biologically, which gives rise to the concept of the reproductive number, which I'll explain right now. But in general, I want to point out that in this area of research, especially when you have conditions involving lots of variables, so in which these conditions are much more complicated, simply putting the condition for which something happens in the model, it's generally insufficient, because the idea is to give a biological insight of that result. So not just to say if this complicated inequality happens, then the population grows. You need to formulate it in a way that makes sense biologically. I mean, using common words. Things like, if life expectancy is this, or if the number of offspring per individual is this, then we have growth or decline, and so on and so forth. So why is this simple rearrangement helping in that regard? Well, there is one basic stuff to know from probability theory, which I'm not going to elaborate at this point, just take it for granted, but it has to do with the exponential distribution. So as it turns out, the reciprocal of the death rate, 1 over the death rate, in this case 1 over mu, is an estimation of life expectancy of that individual. So it's called life expectancy because, again, the meaning of the denominator, or the removal rate from the equation, signifies the death rate, as I mentioned here. But I want you to think in more general terms, in the sense that the reciprocal of the removal rate, because the way people leave one class, one equation if you want, is often via multiple reasons. So, for example, you could leave a certain category in the model via natural death, disease-induced mortality, transfer from one class to another, like for example recovery and so on. So, if you take all the constant removal rates, so for the terms that appear with the negative signs, and you put them at the denominator, so you have 1 over that cumulative removal rate, that'll give you an estimation of the time spent in that category. So here we call it life expectancy simply because it's just the meaning of mu, natural death. But in general, 1 over the removal rate will be the time spent in that category of population, depending what that is. So getting back to the reproductive number, if I view this ratio split into these 3 factors, so interpreted from the point of view of one typical individual, that's the meaning of this 1 here as a factor. So one typical individual multiplied by beta, 1 times beta, will give me the number of offspring per unit of time for one individual. So remember, in the model, beta times p is the offspring from the total population. So if I multiply beta by 1, that'll be just the number of newborns, if you want, per unit of time. So it's a rate, obviously, because it's just per unit of time, but just for one individual. Now if I multiply this number of offspring per unit of time to the life expectancy of the individual, which is 1 over mu, obviously that gives me the number of newborns per individual during his expected lifetime. So at this point, I hope it makes sense why this quantity is called a reproductive number and why it's actually compared to 1 to establish the result. Because to say it's greater than 1 is to say that a typical individual will reproduce beyond replacement. So it will produce more than 1 children during his lifetime. So that means the population will obviously grow. Equal to 1 will be just replacement level. Right? I mean, the population will not neither grow nor decline in that case. So at this point, this is why these quantities are called reproductive numbers. We'll see immediately how that translates to epidemics, and also why they are always compared to 1 because of this this interpretation that, if it's above 1, that's beyond replacement level, so therefore it will grow. And of course, the bigger it is above 1, the faster the population will grow. Alright, so what about the meaning of R naught in the case of epidemics? Well, in the case of epidemics, things are very similar in terms of how they are interpreted. Except here the reproduction refers to the disease being actually reproducing. I mean, in the other words, you view the infection as a way for the pathogen to reproduce. So this is basically defined from the point of view of a single or a typical infected person. And to be more precise, the definition of R naught will be the number of secondary infections caused by an infectious individual introduced in a susceptible healthy population. Susceptible, what I mean is, susceptible means healthy that can be infected, because you could be healthy and immune, right? So that's the meaning of that's what we mean by susceptible, healthy that can be infected. So let's pause for a moment and read again carefully, because many people misinterpret the meaning of this quantity. So first of all, it's an estimation, and again, that estimation is for this particular situation. Imagine you basically place just one infected person in an entirely susceptible population. So a single infected surrounded by healthy people or susceptible people. So you may wonder, well, what's the use of it? Because obviously, while the epidemic progresses, there will be fewer and fewer susceptibles because more and more people will be infected. But remember, this is an estimation of how forceful the disease or the infection spreads in the beginning. And the idea is that as long as the susceptible people are plentiful, so if there are lots of susceptible people in the population, this quantity R naught gives you a pretty good estimation of how many new cases will appear. Although the real number of new cases is not going to be exactly equal to R naught. It's just all about having a good estimation. And as soon as you have few susceptible, so if most of the people are infected, then R naught really loses its usefulness, if you want, because in that case, of course, the probability of meeting an susceptible person is going to be much lower. So, but when that happens, it will be visible in the population that the number of new cases will decline when you reach that stage. Susceptibles essentially are like fuel for the infection. Okay, so let's take a look at this textbook model. This is probably the first model that is presented in math biology courses related to the epidemics, of course, because it's kind of, well, maybe not the simplest one, but the simplest possible epidemic model that contains two main features, the infection and the recovery. So here we have, and otherwise, the model is essentially stripped of all what do you call it? All other features that may complicate the math, but might make it more realistic. So, for example, there is no demographic terms, no birth, no death. This disease doesn't seem to kill anybody, so it's just infection, the transfer from S to I, from susceptible to infected, and recovery rate from the infected class to the recovered class. There's a lot to discuss about how you actually model the transmission. This is one of the easiest, mathematically speaking, form, but there are lots of different forms of how you model the transmission, but all of them, of course, will be related to the size of susceptibles and infected. So in this case, the transmission is essentially proportional, given by this infection rate, proportional to the product of S and I. And one can compute, so first of all, the total population remains constant. If you took calculus 1, if you took calculus 1, it's just straightforward to realize that if I add all the derivatives, you get 0. So that means the derivative of the total population is 0, which means the total population remains constant. And the reproductive number is lambda n over r, and let's see how it's interpreted via the definition I just mentioned. So again, this will be from the point of view of one, in this case, typical infected person, which per unit of time makes contact with lambda n people, assuming they are all susceptible. So notice in the equation, actually, it's lambda s, right? So a proportion of susceptibles. But in the beginning, if the total population is susceptible, then lambda n essentially means the number of contacts that a typical infected person makes per unit of time again. So just 1 times lambda n is new infections per unit of time coming from one individual. And remember in a previous slide what I mentioned about reciprocal of the removal rate. 1 over r will be the time spent in the I class. So I'm not going to call it life expectancy, because the meaning of r is different, is the recovery. So recovery is the removal rate. 1 over r will be time spent in the I class. That is to say, the time being infected, or the duration of the disease, if you want. So new infections per unit of time multiplied by the duration of infection or the disease, that gives me number of secondary cases while per infected individual while that individual is infected. So of course, if it's greater than 1, this quantity, then you will have an epidemic, in the sense that you will have a growth in the number of cases as time goes on, while again susceptibles are plentiful. So let's look at 3 examples for 3 different values of R naught for this model. The first one is for a very fast epidemic when R naught is insanely huge. I chose the value 10. So notice in this case, of course, you have a very rapid increase in the infected class, which is given by the red graph, and at the same time a decline just as fast of the susceptible class. Because in this model, as you saw previously, everybody recovers. The green graph, which is the recovered class, will tell you actually the damage, in the sense that, how many people actually were ultimately infected, because everybody recovers eventually, right? And the fact that the R naught is so big is given by this sharp bump of the infected class. And so if you go back to if we think about what happened a year ago with the SARS-CoV-2 pandemic, when people talked about making sure, slowing the spread so that the hospital capacities doesn't is not overwhelmed, it's essentially all about reducing R naught, not to eliminate the epidemic, but to just make the bump a little bit smaller. Like for example, in the second example here, you have R naught 1.5. The bump is much smaller, so you have a much smaller peak. So if the hospital capacity, let's say, is at 40, then you're good. Whereas in the previous case, you will be overwhelmed. Notice again that if the epidemic is extremely severe, the duration is also shorter, because if the new cases increase very quickly, they just drop the new cases just as quickly. So for example, by the time equal to 3 here, it's already back to the beginning, which was 10, right? We started here with 10 infected individuals. Whereas here, if R naught is smaller, 1.5, it takes longer, maybe until t equals 5 or so, until you get back to the to the beginning number of cases, like 10. Like I said, the starting point is 10 infected people. So a longer duration of the disease, but of course the outcome is better in the sense that fewer people are infected. It's just important for what people can expect, let's say. It's not like, having a shorter disease it's a small consolation, because of course that results in a huge number of cases. But at least you know that it will take a shorter period of time, because the epidemic goes faster. Finally, in my last example, when you have R naught less than 1, 0.6, another maybe possible misconception is that nothing really bad happens. Well, there's no epidemic in the sense that there is no bump, but you still have new cases. By the time it declines from 10 to 0, you still have some infections. And in this case, for example, it's 20, right? In my example here, we have 100 for the total population. So even though R naught is less than 1, you still have some infections until the disease disappears completely. So again, this is for this example in which the disease eventually disappears because everybody recovers. Now, in more complicated models, of course, or more realistic ones, you could have situations in which the disease becomes persistent in the population. So I hope the meaning of R naught is clear enough at this point, and also why, of course, reducing it is one typical, not the only one, but one typical goal of any intervention, if you want. Before we move on to the actual paper that I want to present, I want to give you 2 more textbook examples. We'll spend a little bit less time on this, but just to compare the format of R naught from with the previous one. This model here is similar like the one before. We just added the mortality, like natural mortality, and some demographic term here, a constant source of susceptibles. This is called the recruitment rate, and we can also spend a lot of time discussing its meaning and when it's reasonable to assume that you should have it in the model. Just for simplicity, as a possible explanation for that term, imagine that you have an epidemic in a closed environment, like a campus, for instance, and then you have a constant supply of per unit of time of new susceptibles coming in from outside campus, if you want, so from the outside of that environment that you try to model. So you have a constant supply of susceptibles, and then let's say that the disease takes long enough so that it makes sense to also incorporate natural death. And otherwise, it's the same as before, a disease that doesn't give you any mortality and from which everybody can recover. Now, in this case, one can also prove that the population approaches a constant, not exactly a constant, but approaches a constant in the limit. And the reproductive number is similar to the one before. And I want you to notice that the denominator now is mu plus r. So remember what I mentioned before, that the total removal rate, which is now due to either recovery or the death. So the total removal rate is going to be R plus mu with a negative sign. 1 over that will be now the duration of the disease, so the time spent in the I class. So similar interpretation like before, 1 times lambda n will be new infections per unit of time, and then that's multiplied by the duration of the disease, which is in this case 1 over mu plus R. For my next example, one extra piece from probability, one extra piece that is also well known. When you have multiple removal rates from an equation, these type of ratios in which the numerator is given by one of those removal rates, so these ratios will give you the probability of leaving that class because of the reason given in the numerator. To be more precise, in this case, you leave the infected class via death or via recovery. So this ratio gives you the probability that an infected individual dies before recovery, or the fraction of infected people that die before they recover, and R over mu plus R. So if you have the recovery on the top, that will be the fraction of the probability that an infected individual recovers before natural death. This will come actually important again when one tries to interpret that R naught from a biological perspective. So, and here's a quick example that justifies just what I mentioned right now. This is yet another modification of the basic model that we had in the previous slide, except now I don't have recovery. So in this case, this will be like a disease which doesn't provide any recovery at all, but we have vaccination. So we have a transfer given by delta S from the susceptible to the vaccinated class. This will be an example of a perfect vaccine if you want, because the vaccinated people don't participate in the infection, so they cannot be infected. And if you look at the reproductive number, it looks very similar, but you might be confused if you followed me up until this point, because you would say, well, wait a second, but 1 over mu plus delta is not going to be the removal. I mean, it's not the expected lifetime of the disease. It's not the duration of the disease, because delta is not in the infected class. And you mentioned that, you know, the R naught is from the point of view of an infected individual. But if we just multiply and divide by mu, so if we make some rearrangement of the terms here and some algebra tricks, if you want, so multiplying and divided by mu, it's an equivalent expression. But if we look now at all these factors from left to right, now with a little bit of carefulness, if you want, to interpret the coefficients here, it'll make sense that this is indeed the R naught that you would expect. So let's see again how this goes. Again, one typical infected person will make contact with a proportion of the total population assumed healthy. But remember, now susceptibles are vaccinated at the same time, so there will be a probability of some of them not being vaccinated. So only those not vaccinated will be truly susceptible of the disease. So this number of people that one infected person makes contact with, only a fraction of them, given by this ratio, will be susceptibles, that is to say not vaccinated. And therefore these three factors will give me the number of secondary infections per unit of time. And then finally we multiply by the duration of the disease, which is 1 over mu, because again mu is the only removal rate from the I class. So I put this example, this is the last example before the actual paper itself that I try to present here, because it's important to notice that the simplified mathematical form of the R naught is often not the one that actually can be interpreted biologically. So the simplest possible math might be the most confusing one if you try to get some sense of what goes on in the population to, again, formulate that result in meaningful terms. So this multiplying and divided by mu was not just for the sake of it, but was because of this need to interpret it. And you will see in the paper that a more dramatic example in which you will have to make lots of rearrangements for that to work. So you can give that interpretation. So before we move on to the actual paper, an important remark that I want you to keep in mind, because that will be connected to the unusual or the unexpected result, is that what is expected pretty much all the time is that this R naught will move in a certain direction expected that if you increase the recovery or the vaccination. You can increase the recovery via treatment, for example, if available. So notice both the recovery and the vaccination appear at the denominator. So if I increase either of the two, if I increase the vaccination, if I increase the recovery, R naught will decrease. And that will be expected. No surprises here. It won't be even a paper, right? I mean, it's nothing spectacular to say if I increase the vaccination rate, I'll get fewer number of secondary cases. That is what is expected when such a policy is implemented. And obviously, you will see that often the situation is the opposite, because that's the whole point to again keep on giving you previews of coming attractions, so to speak. So this is why I want you to have this in mind, because the opposite will happen under a certain particular situation, which I'll talk about in a couple of minutes. Now, before I introduce the model, let's talk about risk behavior in epidemics. So the reality is that what influences the contact rate is also the risk assessment that each individual undertakes with respect to the disease itself. So this is one of those concepts actually which are certain to exist. Almost you don't need a proof, because each and every one of us is a proof. Every one of us realizes, right, if we have a little introspection, that we engage in risk behavior, in the sense that we assess the situation and we say, okay, am I vaccinated? Then maybe I can go out in society more often. I can travel because I'm protected. Do I wear a mask? Is the mask really a good one, or is it just a flimsy one? So depending on that, my or one individual willingness, for example, to approach another person or to come closer to other person may change because of that. So in general, one can talk about risk avoidance or risk taking, right? So like I said already, vaccination typically leads to risk taking. Indeed, vaccination is actually advertised as a way to engage in risk taking. More social interaction, like I said, no more masks, travel, and so on. Now, the problem is, of course, to anticipate the model itself, is that the effectiveness of vaccination may be not the one that you may expect. So the person engaging in risk-taking might have a mismatch between how much risk-taking he or she is engaging in with respect to the true vaccination protection. Not to mention, of course, that the vaccination protection may change over time. It may wane, as we know already. Actually, at the time when I give this talk, it's the whole discussion is about the Pfizer vaccination for COVID losing its effectiveness after a couple of months. So treatment availability, of course, is the reason for engaging in risk-taking. Antibiotics, of course, is a good example of people not fearing mortal diseases in the past. With respect to risk avoidance, some examples from the past. For example, the HIV pandemic in the 80s made huge differences in risk-taking, or lots of awareness about sexually transmitted diseases, and of course behavior related to risk avoidance in that area. And of course, disease symptoms. The more virulent a disease is, the more fear people will have, right? So then they will engage in more protective measures. If the disease will be just a nuisance, of course, nobody will care as much. Okay, so let's go back to the math. How do we actually model the risk avoidance or risk taking? Again, there are lots of ways to do this, but mathematically, the easiest way is via these modifiers of the transmission risk, of the baseline transmission risk. So if we take lambda as the baseline or normal risk taking, or the baseline risk taking, we can model the extra risk taking or risk avoidance by using these extra factors, which I'm going to actually ask you to try to focus on from now on, and don't have to really focus too much on other variables, because I'm going to use these often in the next slides. So for risk avoidance, we can simulate that with a quantity between 0 and 1, eta between 0 and 1. So the closer to 0 eta is, the more risk reduction we have. So for example, if eta is equal to 0, that'll be basically a complete avoidance of infection. And risk taking will be given by epsilon greater than 1, which is essentially any quantity greater than 1, because that will be an augmenting factor, right? I mean, that will indicate risk taking, so an increase in the transmission risk. So if that's all there is to it, that is still nothing really worth actually making a new model with it, because obviously, eta and epsilon can be actually part of lambda. I mean, if there are now no changes or nothing unusual in the future of the model, this can be part of lambda. The problem is, of course, is that there will be actually different type of risk levels, as you will see in the actual model, and there will be transitions from one risk group to another, and the way the different risk groups interact actually matters. So in the model that is the subject of this paper, and at this point I should again mention here one more time that this was written in 2016, so the motivating disease that we had in mind here was not SARS-CoV-2, obviously, right, in 2016. So this was a disease without recovery, but the main result still holds if you add a recovered class, although the conditions are probably different. So I'm actually working now to rewrite this paper, to come up with a model specific to the COVID disease infection, that to see if to what extent and what conditions are needed to have the same type of result that I'm presenting right now. Alright, so this model contains, like I said, a disease without recovery, but for which there is a partially effective vaccine. So vaccinated people can still be infected, but a lower rate. And we also assume that infected people can stay a considerable amount of time without being aware that they are infectious. So this can happen because of the lack of symptoms or incubation period or any reasons that will delay essentially one infected person being aware that he or she is infected. So, and we'll also assume that those who are vaccinated are subject to risk taking. So because they are vaccinated, they engage in high risk taking. So with that in mind, we have essentially 5 different types of people in the model. So we have the susceptible not vaccinated. Those are the normal risk-taking people. And we have the infected not vaccinated but not yet diagnosed. These will also be of the same risk level, normal or baseline risk level. That's why I call it IN. Then we're going to have the susceptible and the vaccinated. Those will be the high-risk people. And of course the infected, vaccinated but not yet diagnosed, which again will have the same high risk taking. And finally the diagnosed people, which will be actually subject to risk avoidance. So a diagnosed person is expected obviously to engage in risk avoidance because that person is aware of the infection itself. So, in terms of how we modify the baseline infection rate because of these assumptions, there will be three variables again that I want to focus on. The vaccine efficacy, which is the amount of reduction of transmission given by this Xi. So the closer Xi is to 0, the better the vaccine is. So Xi equal to 0 will be a perfect vaccine, will be no transmission at all. Closer to 1 will be essentially a useless vaccine, like no effect. Risk-taking greater than 1, the diagnosed risk avoidance will be between 0 and 1. So we have various types of transmission, and I want you to see how these modifiers of the transmission term actually act against each other in the same transmission group, if you want. So we have the normal baseline risk, right, between susceptible and infected, both of them not vaccinated. But if we have only one of the persons that interact vaccinated, then we already have the augmenting factor epsilon because of the risk taking. So this one, for example, the second pair will be a susceptible not vaccinated. That'll be with baseline normal risk behavior, and IH, which will be vaccinated infected person. And of course, since it's infected, the vaccine effect is lost, and therefore you have risk taking only, epsilon greater than 1. If we have susceptible vaccinated and infected non-vaccinated, we still have risk taking because of the susceptible guy, but the infected not vaccinated, the other way around. The infected not vaccinated will be engaging in how do I say that? The susceptible vaccinated, yes. Yeah, the susceptible that is vaccinated comes with both the vaccine effectiveness, which is given by Xi, and of course the risk-taking epsilon. So these two, of course, are playing against each other, right? I mean, Xi will reduce the transmission risk, epsilon will augment it. So I mean, I want to see already that these two play against each other. So whether actually you end up with something greater than the baseline risk or lower, it really depends on how much risk-taking happens with respect to how really how effective the vaccine is. Because you could have a big, a very effective vaccine and not a lot of risk-taking, and that will still cause this to be less than lambda. The problem will appear, of course, as the vaccine effectiveness will be lost in time. I mean, gradually, of course. I mean, not completely lost, but not as effective as it is in the beginning, let's say. So what I called cumulative risk behavior is when two individuals which are in the high risk group make contact and an infection happens. So this will be essentially a susceptible vaccinated, an infected vaccinated not aware of the disease. So these two individuals, each of them comes with its own augmenting factor because of the risk taking. So you have this epsilon squared, which I call it cumulative risk taking because it's a reinforcement of the risk taking from both individuals. So if you want a quick analogy with the masks, it's like the difference between two persons, both without the mask, one susceptible, one infected, as opposed to one wearing a mask and one that doesn't wear a mask. So if you have only one not wearing the mask, that's one effect of the risk taking. But if you have both of them not wearing the mask, then you have this cumulative risk taking. It's not just about masks, of course, but this is just an example. And then, for example, with the diagnosed, of course, you also have the reduction of the transmission because of the diagnosed, but again, that's also superimposed with risk taking from the susceptible, the effect of the vaccine, and so on. But the unusual result that we will come to pretty soon is actually related to this cumulative high risk taking effect that I highlighted here. All right, so I don't think I'm going to spend too much time on this model. You can pause if you want, because I want to focus on the main result. These are the transmission terms. There are some demographic terms here. This is the disease mortality. This is the natural mortality that appears in every equation. Diagnosing rate given by D. With all of these together, there's the reproductive number format, which again I'm not going to spend too much time deciphering each of the variables. I'll focus on the overall meaning because that's going to be sufficient. But as I told you before, the format you see here, which is the simplified math format, it's not the one that is actually useful from a biological interpretation perspective. This one actually is. It's equivalent to the first, but this one in this spread out form is suitable for biological interpretation. Based on what we discussed so far, you might recognize here the proportion of the non-vaccinated people. This is the proportion of vaccinated people. Remember, delta and is the vaccination rate. So if you look at these two quantities, two big quantities that are added together, it turns out that R naught is essentially made of the sum of two components. Rn, the first component, is the secondary cases of non-vaccinated infected people. And the second component, Rh, is the secondary cases of vaccinated infected people. So whether the R naught is greater than 1 or less than 1, of course, depends on how each of these are with respect to, how big each of these Rn and Rh are. But both of them, each of them separately have this meaning. Because remember, when I said before that R naught is from the point of view of a typical infectious person, but because of the risk-taking groups, different risk behavior, you have essentially two different types of infected people that play a role in the epidemic. Maybe even maybe even better to actually understand the meaning of each of these two components is to look at a schematic, if you want. Again, let's go back again to the meaning of R naught as secondary cases of an infected person. So that is to say, in how many ways one infected person makes copies of itself, if you want. So if you take, to talk about Rn, right, the one corresponding to the non-vaccinated people, a typical infected non-vaccinated can make a replica of itself by infecting directly a non-vaccinated susceptible, or indirectly by diagnosing first, J is the diagnosed class, and then a non-vaccinated susceptible. These are the only two routes of creating a secondary case of IN. There's no risk-taking in this region, right? It's just risk avoidance because of the diagnosed. The second part, RH, same idea. In how many ways a typical vaccinated infected person makes a replica of itself via direct infection of a vaccinated susceptible or via diagnosing. This direct route, this is due to cumulative risk-taking. This is the one that is subject to cumulative risk-taking because of those two individuals. So that's the meaning of the second term. So we finally get to the highlight of the talk. What is that unintended consequence? Well, first of all, that unintended consequence, it's important in order to understand why that happens, because it will be very unusual when you hear it. It'll happen when the cumulative risk-taking is the driver of the epidemic. So in other words, if that component of Rn, the one that is related to the high-risk group, is greater than 1, and when the component from the normal risk-taking is less than 1. So this actually appears if you look at these two conditions. Remember, Xi is the vaccine efficiency and epsilon is the risk taking. So this happens for some intermediate values of risk taking with respect to the vaccine effectiveness. So when this situation happens and you compare R naught before and after the introduction of the vaccination, it turns out that R naught in fact will increase if we have too much risk avoidance from the diagnosed. So it turns out that risk avoidance, too much risk avoidance, in other words, if eta, remember eta is the reduction of the transmission because of the diagnosed. So if eta actually comes very close to zero, so if it drops below a threshold, which is given by this expression, if that happens, as a matter of fact, you have a worse situation, an increase in R naught, once you introduce the vaccine. Again, provided that the effectiveness of the vaccine and the risk taking is in such a way to create this situation. So this is very unusual, and of course it requires quite a lot of discussion and explanation, because on the face of it, it doesn't make any sense. Basically, I mean, how come? Because essentially, what you would say is, well, if the diagnosed people in fact completely avoid infection, well, it's kind of guaranteed that R naught will increase, because once you are in this condition. So I think it's useful to think about some analogies to understand why that happens. But even before I do that, I want to point out that the reason this is happening, it's not because reduction of the risk of the disease is inherently bad. I mean, of course, it's always good for the individual if it avoids infecting another individual. Of course, that's basically good. But the unwanted effect is essentially a demographic effect at population level, or a population dynamics effect for the whole population. The idea is that while the diagnosed people still mingle in the population with the high-risk people, they manage to essentially dilute the contacts between the high-risk people. So essentially, by managing to infect some susceptibles, high-risk susceptibles, it turns out that it breaks essentially the strong reproduction level between the two high-risk groups. So it's a perverse effect in the sense that by removing themselves completely from the infection, they simply leave too many opportunities of contact between the high-risk groups. So once that happens, there are lots of contacts in the high-risk groups, and if that part of the reproductive number is greater than 1, then you will have essentially a spike in the secondary cases. So if it's still not clear, I'm gonna have here now an attempt of a little bit of art, not too great, but I hope the analogy is gonna be good enough to make the point, so to speak. So imagine you have essentially a fire where you have similar types of wood, pellets of wood, some of them wet, some of them dry. So the D represents a dry wood, W a wet wood. And then so there's a fire that's one of them catches fire, and then the fire starts to spread. And so suppose that you want to essentially control the fire by removing some of the wood here. And let's say you decide, for some reasons, to remove some of the wet pieces of wood, like you see here. Will that actually make the fire worse or bad? Well, to continue with this kind of thought experiment, you could think that the wet wood, acts kind of like a damper on the flame. So, for example, if the fire starts here, this D here, it'll catch fire, but these two, the first and the second from the left pieces of dry wood, although they're kind of close to each other, between them there is a wet piece of wood. It may or may not catch fire, but if it does catch fire, maybe it's not going to burn that quickly, or maybe it will be a slow burn, and then this one won't catch fire after all. So this is by no means a perfect analogy, but I want you to see the effect of being present in the burning fire pit essentially for the overall size of the flame. So by removing these wet pieces of wood, I simply made the proximity between the remaining dry wood, I make the likelihood of them catching fire much higher because the dry wood that is left, it's still close enough to each other. On the other hand, if you look at the third row here, if the distance between the dry wood is big enough, and you have lots of wet wood, you can remove the wet wood, and of course, the dry wood is farther from each other, so maybe in that case the flame will not grow higher. So I mentioned these examples. I put this example to indicate that it's not a judgment on whether it's a good idea to save a piece of wood or not. Because once you remove a piece of wood, of course you save it, but the overall flame may be actually worse if you do that. Now, of course, an immediate question you may have is, well, why don't you remove the dry wood? But again, if we make the analogy between high-risk people, so the dry wood will be like the high-risk people, and the wet wood will be the diagnosed individuals. The question is whether one can do that. And I will argue that risk-taking in many cases cannot be actually controlled or avoided. Maybe controlled but not avoided. It's completely unrealistic to expect people to vaccinate, for instance, and have the same risk avoidance as before. I mean, that's just not going to happen. The only question is how much risk-taking will happen. If you are still not convinced about this type of demographic effect, this has nothing to do with the topic of the paper, but there's something in ecology called sterile insect technique method for controlling biological insects, undesirable insects. For example, there are some flies that lay eggs in wounds of animals and then they get sick and so on. So anyway, so you have a insect population that you try to reduce, and the sterile insect control method consists in capturing, first of all, male insects, which are sterilized via radiation and then released in the population where they compete with the existing males for reproduction with female insects. So what's important here to understand is that the reason why that works is because there is a dilution effect of the possible fertile matings. So the female insect doesn't distinguish between the male sterile and the fertile male. The female will reproduce once per cycle, and then of course if she mates with a sterile male, there is not going to be any reproduction. But the key thing that is kind of connected to the result from my paper is that the radiation needs to be strong enough to sterilize, but not too strong to decrease physical fitness. So you actually need these guys to be in the population to mingle and kind of upset the fertile contacts, to reduce the probability of the fertile contacts. So this is kind of the mechanism that happens here in the epidemic. It's good that diagnosed people actually avoid infection. I mean, they engage in risk avoidance, but as a matter of fact, their presence, as low, if it's still there, it will dilute the contacts between the high risk groups. So if they are actually completely absent, then you just basically leave the opportunity for the high risk groups to take over essentially, and then increase the reproductive number. So I'm going to give you here a couple of simulations for this result. What you see here is a diagram of possible values of the risk avoidance eta with respect to the risk-taking epsilon. So epsilon is greater than 1 always, and eta between 0 and 1. So the dark region is the intended outcome. So it's the region in which you have a reduction in R naught as intended. And this picture is for various level of vaccine effectiveness. So in this case, we're going to start with a very lousy vaccine, right? So Xi 0.8 means a very small reduction. From 1 to 0.8, it's a very small reduction of the infection, of the transmission. So if the vaccine is really, really lousy, notice it takes very little risk-taking to get that undesirable effect. So let's see again how we can interpret this diagram. The important part is the one below the curve here, right? So again, remember the dark region is going to be the desired outcome. So if I move vertically, let's say the risk taking is 1.15, somewhere between 1.1 and 1.2. If the risk avoidance drops below, let's say 0.1, so and then lands in the white region here, that means R naught will increase. So if the risk avoidance is below 0.1, eta between 0.1, then you have the unwanted consequence. So unwanted consequence is any region below this curved line. If the risk taking is not too much, let's say 1.02 or whatever, then you could do, eta can be any value. So diagnosed people can do whatever they want. R naught will decrease as intended. So if the vaccine is very lousy, it's very little risk taking necessary to actually get the unintended consequence. As the effectiveness of the vaccine drops, so if C is 0.6, so it's like 40% drop, or nearly, well, let's actually move on to just half, right? So let's say drops by 50% the vaccine effectiveness. No, the other way around, I'm sorry. It's better than before. So this one, because the first one was really lousy, this one is a little bit better, right? Like an intermediate level of effectiveness. Well, in this case, the risk taking should be below like 1.5, 1.6 for the unwanted effect to happen. So if the risk taking is not too big, so if it's like 1.1, 1.2, 1.3, all is good. Any values of eta will be in the dark region. As soon as you move to, let's say, 1.6 risk taking, all of a sudden, if eta drops below this level here, then you have an increase in R naught. And as you can realize, the better the vaccine is, so let's look at a nearly perfect vaccine, right? When X is very close to 0, so it will be a nearly complete avoidance of the disease. It will take an exaggerated amount of risk taking to get the unwanted result. So this will be basically perfectly fine for all practical reasons, because nobody will increase his risk taking by tenfold, essentially, right? That's not realistic. So probably the risk taking is somewhere in between 1 and 2, 3, maybe somewhere here. But the whole issue and the importance and the connection with the current events with the vaccination for SARS-CoV-2 is no matter how good the vaccine is in the beginning, right? So let's say it's 90%, something like this. And let's say the risk taking because of vaccination is 1.5 or twofold, all good. But as the vaccine effectiveness wanes, then that risk taking level, all of a sudden is in the bad region, and then you have an increase in R naught. So actually, I'm very interested to see if there could be done some modeling to actually see things like that can explain, for example, what happened in Israel with lots of cases, after months after full vaccination. So with that, let's go over a quick summary so that make sure that we don't get the wrong conclusion from this presentation. So it's not like the policy should be to recommend people to actually infect more, because this is essentially talking about an unwanted consequence, but the answer, of course, is not to essentially say, okay, just infect more so that you don't get this unwanted effect. The idea is to, of course, be aware that it can happen, and figure out or try to reduce the risk-taking level with respect to the vaccination. So in fact, I would argue that if the awareness of the true effectiveness of the vaccine is clear, probably people will engage accordingly in an appropriate risk-taking. So for example, if we know for sure that the vaccine is going to be weaker and weaker, then we have more reasons essentially to engage in avoidance. The whole idea is to essentially not have a mismatch between the true effectiveness of the vaccine and the risk taking level. So the self-quarantine, of course, is always good because each contact has a lower chance of infection. But the main lesson from this presentation is that when the infection is actually spread through multiple risk level, the interaction that sustained the epidemic is important, which is the cumulative risk-taking effect. And so any feature that dilutes the contacts will reduce the R naught. And as it happens, basically the participation of the diagnosed can have this perverse effect that will cause an increase in R naught. And so this is the case in which cumulative risk compensation can change a future, such as quarantine or risk avoidance, from a positive role to both the individual and the population into a negative role at the population level. So at the individual level it's still good, but at the population level can have this perverse effect. So another last message which I think it's important, and unfortunately it's completely ignored nowadays. When there is a policy measure of any kind, just vaccination, quarantine, whatever, a question like, is that good or bad, or will that intervention succeed? Even if we put aside the fact that one should be very specific on what the goal is, in this case, for example, the goal could be the reduction of the R-naught. The reality is that often there is no straightforward yes or no answer. And even if it's against our strongest intuition, we should really realize that it's just not a question of yes or no. It's too complex for that to be the case. And so, of course, one needs sufficient humility to realize this and to at least be aware and for these possibilities to happen, the unwanted consequences. And so also there should be a recognition between what can be done and should be done, right? So, because if we go again by my model, you could say that the best course of action again is reduction completely of the risk taking, but that can work up to a certain extent. Again, I firmly believe, and I think most people will probably agree with me, that it's just not realistic to impose or to expect vaccinated people to not engage in risk taking. It's just not going to happen. And indeed, the vaccination was promoted as a way to actually engage in more risk taking. I think the nuance here is to actually be honest as the vaccine effectiveness wanes, to essentially tell the truth. Like, okay, well, 5 months ago you could do this, but 5 months later the vaccine is not that good, so therefore you have to protect more, and so on. And another thing that maybe can actually be is the subject of an entire different talk. What comes first, the interest of the individual or the population? Because they often do not overlap. The interest of each individual with respect to the individual interest of the population. Okay, so if you have any questions, you can leave them in the comments. And as I said before, there's a short course on math modeling, which is uploaded on my channel. If you want to take it, if you are a potential student, or even if you're not, you can go through it if you're interested in the topic itself. So here, this is the paper in question, and my website where my research is posted. And thank you for your attention.